Welcome everybody. In this lecture, we will be discussing about Smith chart. Smith chart is a very powerful and convenient tool for solving transmission line problems. This chart was invented by Philip H. Smith in 1930s. It is a graphical means for solving transmission lines problems. Also, it can be used for antenna and resonance problems too. It is extensively used in microwave design during the Second World War. I want to discuss about how the Smith chart was developed. So let us start with the reflection expression. Gamma equal to ZL minus Z naught, ZL plus Z naught. We can rewrite this expression to this gamma L over Z naught is equal to 1 plus gamma L or minus gamma L. Then we just write down ZL over Z naught equal to lowercase ZL Z naught, and that is called normalized load impedance. So then we have, as you know, it is an impedance. It might have a real part and imaginary part. So we write R and JX. R is the normalized resistance and X is the normalized impedance. And also the reflection coefficient might have a real part and imaginary part. So uh, now we multiply both sides with this factor. So 1 minus gamma L j gamma I. So multiply both sides with this factor. So once you multiply this, you can rewrite this. So 1 plus gamma I squared minus gamma R squared and 1 minus gamma R squared plus gamma I squared. So then you simplify this, you might come up with this one. So from this expression, you see R is the real part. It can be equated with this real part. So it is gamma R square and Ri square and Rr square. This is the real part. So and X can be equated with this part. So now we can write R equal to like 1 minus gamma R square minus gamma R square of this, and X can be written like 2 gamma I 1 minus R square R square. So we separate it in two parts. So the part without J is the real part, that is equal to R, and with J part is the imaginary part, that is equal to X. So we got R and X now. So from this R, we can again simplify this to get an expression like this. So if you think about this expression, this is nothing but the expression of a circle with center at this point and 0. So center has the x values here and y values is 0 and radius is this. Similarly, x can be written with another expression of a circle. So with radius 1 and 1 over x, and sorry, the center 1 and 1 over x and radius is 1 over x. So now we can draw two circles. One is the R circles and another is the X circles. So we know the center is this point, and this is the radius for R circles, and this is the center for X circles, and this is the radius for X circles. The radius is varies with X, and center also varies with X. And here the center point also varies with R, and radius also varies with R. Now let us draw the R circles. So R circles have got an expression like this. Now if I choose a different value for R, 0, 0.5, 1, 2, 5, infinity, then the radius will be 1 over 1 over R. So that is 1, 2 over 3, 1 third, 2 over 3, 1 over 2, 1 over 3, 1 over 6, like 0. And the center will be, if R equal to 0, the center will be 0, 0, 1 third 0, 1 half 0, 2 third 0, 5, 6, 0, 1, 0, like this. Now let me draw the circles now. So let us think this is my uh, imaginary axis, this is my real axis. So now I put the first circle, that is R equal to 0 circle. R equal to 0 circle, the center is 0, 0 and radius is 1. So I write R equal to 0 circle here. Now if I draw R equal to 1 half circle, so R equal to 1 half, this circle is will be center is here. Center is now. So now r equal to 1 circle, the center is here like this, and r equal to 2 circles, the center is at this point and radius 2 over 3 this. If you put r equal to 5 circles, now we got the, you see, for all the r circles is touching this point. So there are, these are the r locus. This value, this circles has constant value for r. This has constant value for r. They are, all of them has equal value for r's. Now, if we want to draw the art circles here, so if you see how to draw art circles, so let us take a big circle here, and then I put 0, 0. This is my center 0, 0. Then first circle will have the center here, second circle will have center here, third circle will have center here, and so on. So I draw the second circle, third circle. So like this. So you got the R circle. So if you want to find more values of R in between this, so you have to put more circles here. So you can put a lot of circles here depending on how how many different value you want to choose in between these 2 points. For example, this is R equal to 1, this is R equal to zero point 0.5. If you want to make mm, uh, zero point 0.6, 0.7, zero point 0.8, zero point 0.9, then on. So you can make more circles here. Similarly, this is R equal to zero point 0.5, this is R equal to just 1/3. So you can put the point. Similarly, if you draw the x circles, you see x circles has the values x equal to 1. X might have a positive and negative because x could be inductive or capacitive. So if x equal to 1 half, x equal to 1, 2, 5, infinity, then radius will be have this value and center will be this. So you see, if the x circles you put here, you will get like now, get circles like this, like a 8 figure, right? Figure of 8. So now R circles and X circles, if you put together, then you will get the X circles are here on this line. We have, so on this line you have constant value for X. On these lines you have constant value of X. So all the circles are just emerging from this point, and X circles are going this way, X lines are going this way, and R lines are going this way. So make the circular lines and X line pointing outward. So now I am taking this, there is no R values, right? Only X values. So I am taking the common part of this, where R and X both exist. So these are the common part. This is the common part where both R and X exist. So just we take this one to produce a Smith chart. So the Smith chart is basically look like this. This is a nice Smith chart here. You see these values are uh, x values here. So x values 0 0.2, 0 0.5, 1, 2, 5 like this. So this negative 5, negative 2. So all those negative 2 lines are here. Negative 1 lines is this, negative 2 lines is this, negative 5 lines, positive 5, positive 2, positive 8. These are the x values here. You see x values are labeled on this. And these are the r values. So this is r equal to 0, then r equal to 2, r equal to 0 0.5, down to 5 like this. Now, how to use this? So this point has R and X both 0, so that is called short circuit point. And here R and X both are infinity, so that's the open circuit point. So this is the open circuit point, this is my short circuit point. And this side is inductive and this side is capacitive because X is positive here and X value will be negative here. Now, how we can use Smith chart for solving transmission line problems. So to solve this, like let us assume we have a load impedance 50 plus J100 and the line impedance, characteristic impedance is 100 ohms. So now what you have to do first? So you see 50 and 100 you will not find on this chart. So what you have to do, you have to normalize this value. So just divide the values by 100, the characteristic impedance, you will get the normalized value. So normalized value is 0.5 and 1. Now you see R is zero point 0.5, X is 1. So you see R is zero point 0.5, R is this value zero point 0.5 and X is 1. So they are intersecting at this point. So this is my zero point 0.5 line here and this is my on line here, so they are intersecting here. So this is the point for ZL. So this is the ZL point. So on the Smith chart uh, we can locate the ZL point here. So similarly, if you have a ZL 0.16 and 0.34, so now you see 16 and 0.34. So to see 16, so how we can find 16? So we need more points because 16 and 34 cannot be obtained accurately by using the Smith chart we showed before. But this has a more precise points here, so we can get these numbers accurately. So at first, this is my center of the Smith chart. So this has 1.0 here. This is the center of the Smith chart, and from this center just you see, we have to find 0.16 and 34. So real value is 16. You can see this is zero point 0.1, zero point 0.2. So 0.16 will be 121416 here. So 0.16 is this line. Now you have to see 0.34. So this is 0.1, 0.2, 0.3 and this 0.4. So 0.34 will go on to this line. So 3, 4 is this line. So now you see the both line intersect at this point. So this will be my ZL point. So this is my ZL point. If you want to show 0.36 at 0.22, so 0.36 will be 3. So I am showing 0.32, 0.22 now. Yeah, this is my 0.22 and this is my 0.36. So they intersect here. So this is my ZL point for the second case. Now we also can find the reflection coefficient. So how to find the reflection coefficient? From the center and the ZL point you draw a circle. This circle is called reflection magnitude circle. So let's say this is your ZL point and this is the center. So you draw a circle uh, uh, putting your center here and this is the radius. Draw a circle, and once you draw this circle at this point where the circle pass through the or cross the real axis or the R axis, you see the V maximum at this point or current will be minimum, and you can also find SWR value from there, and you also can find HWR value from here. You don't need to draw HWR circle. However, without drawing HWR circle, you will get the HWR value from here. And at this point, the point at the uh, opposite to this point, it has the voltage minimum and current maximum. Sometimes we might ask you to locate the point where voltage has the maximum value. So at this point we have the maximum voltage point, and this has the minimum uh, voltage point. And if you start from here, if you move this direction, this is called toward the generator. So we are going toward the generator point. So this is your load, you are going to the generator, and this is the load. This region is capacitive region, this is inductive region. So now this is the complete Smith chart. You see, this is the complete Smith chart. So this is the chart, and here we have lot of measure scales here. So you can measure a lot of parameters from this scale too. So you can see this scale. So you can measure from this scale. You can measure the reflection coefficient, the standing wave ratio, and these values. So this is the complete Smith chart. Now this Smith chart can be used for impedance and admittance measurement. So if you want to find the impedance or the admittance, so load impedance, input impedance, or input admittance, you can use this Smith chart. You can use this Smith chart for finding a standing wave ratio. You can use this for finding the reflection coefficient at load, input, or any point. And also it gives the magnitude and phase angle of this reflection coefficient. You can locate the minimum and maximum voltage or current or impedance point. As it is said that when voltage is maximum, impedance will be maximum too, because voltage maximum, current minimum gives you impedance maximum. Impedance equal to voltage over current. So impedance will be maximum if voltage is maximum, current is minimum. Similarly, impedance will be minimum when voltage minimum and current maximum. So at the point at the right, it has the maximum voltage, maximum impedance. Point at left will have the minimum voltage, maximum current, minimum impedance. And you can find the location of source, and also you can design meshing system. So now what you have to do to use Smith chart, you have to know the scales available on the chart. Suppose how to find the R, how to find the X, how to find the reflection, how to find the standing wave ratio, how to find the admittance, how to find the maximum voltage, minimum voltage point, like this. And then you have to normalize the impedance or admittance. You have to do that. How to normalize the impedance? ZL divided by Z naught, you will get the normalized impedance. And for admittance, you multiply YL with Z naught, you will get the normalized admittance. Similarly, for converting, and then also the length, distance or length, also measured in terms of wavelength. So the length should be measured in, or length or distance should be measured in terms of wavelength. And after collecting the information from each Smith chart, we have to redo the process. For example, normalized, you have to denormalized, because to get the actual value. Similarly, the length or distance, you have to convert back to in meter. Now here meter will be converted to wavelength, then the wavelength will be converted back to meter. So now let us find the chart scale. So the real part or R values can be obtained from these scales. These numbers basically indicate the real part, and the imaginary part is indicated from here. So you get the imaginary part. Sometimes these values are given, also written here, also written here, also written here. So these are the basically this value is also copied here. So this is the R value is also copied here. The R value is also copied here, and the X values also copied here too. So you see the X values from here are also they are copied here. The R values are copied here too. So the imaginary part you can get obtained from this expression. So the top part will gives you positive x, that is the inductive part, and the bottom part will gives you the capacitive x, that is the negative x or capacitive values. And we also use the reflection coefficient magnitude from here. So for example, you get reflection coefficient, but you cannot measure reflection coefficient from here. It is a radial distance from here, you can measure it from this. So for example, you have a value here. So the reflection coefficient you can measure from this scale. And the angle of reflection, there is some angle terms here. There you see the angle scales will be shown here. So just they are starting from 10 degree, 20 degree, 30 degree, 40 degree, like this. So you can find the angle of reflection from this scale. And then you can find the standing wave ratio over here, the standing wave ratio. You also can get it from here, but also get from here. So standing wave ratio you can get from the real value of this, starting from 1, because the standing wave ratio cannot be less than 1. So it must be written from 1 to this way, or also from this scale. Now, so if you start from, you want to find distance or location in wavelength. So there is the wavelength scale here. So you see this scale is the wavelength scale here. The wavelength scale also written here. This is the wavelength scale. And you can find the distance in wavelength. by from here from this scale. But if you are starting from load ZL, for example, you got your ZL somewhere here and you want to find Z in. So from ZL you have to move toward the generator. Toward the generator means this direction, clockwise. Toward the generator means you have to move clockwise. So from ZL, let's say you find your ZL here and then you move this way. How far? So you move this mass. Let's say this mass is equal to 5 meter and 5 meter is 2 wavelength. So you have to go 2 wavelength from here, 2 wavelength from here, and you'll find then Z in. But if you are working at Z in, let's say your Z in is here, then you want to find ZL. So from Z in, you have to move toward the load. So you have to move toward the load this way until you will find ZL. So sometimes ZL will be given and you need to find Z in. So if ZL is given, from this given point, you have to move clockwise direction to get the input impedance. And if some input impedance is known or given, then you have to move anti-clockwise direction to get the ZL. Because you are here, then you have to go in anti-clockwise direction, in this direction, toward the load direction, get the load. Now, just for this particular Smith chart, we have few more scales here, but for this course we don't need them. So we need only standing wave ratio and reflection coefficient scale from down here, and the other scales from here. So other scales here we have R scale, we have XX scale, we have angle scale, wavelength scale. So now we also shows you how where is the B max, B mean and Z max located in this way, and B mean, I mean, Z mean located will be located at this point, and this is called ZSC. So this is ZSC point or YOC point, and this is ZOC point, YSC point. If you see that ZSC is the short circuit impedance, and opposite to this will be short circuit admittance, and YOC is the open circuit admittance, and ZOC is the short circuit, sorry, open circuit impedance. Open circuit impedance is infinity, so this is the infinity point. And if impedance is infinity, then uh, admittance will be zero, and zero is here. Similarly, short circuit impedance is there because short circuit impedance is zero, but short circuit admittance will be infinity. So short circuit admittance is there. So Z, the opposite to the Z is Y, or opposite to the Y is Z. You need to have this type of tools for solving Smith chart problem: a compass, a ruler or a scale, a sharpener, eraser, and a pencil. So let us solve this problem with using a Smith chart. So you have a load of 100 and 150 ohms with a 75 ohms characteristic impedance. So 75 ohms to a 75 ohms characteristic impedance on 0.8 meter long transmission line in 60 megahertz. U is zero point 0.6 C on the line. Calculate the reflection coefficient, standing wave ratio, input impedance at generator, load admittance, location of Vmax and Vmin, and input impedance at 1.2 meter from the load. So just at first you see the load impedance is this, and characteristic impedance is 75. So what we have to do, we have to normalize this value. So I am showing you. So the ZL is given and Z no is given. So now I find the normalized impedance lowercase ZL, that is 1.33 Z2. Now I am showing 1.33. So you see 1.33 and Z2 is here 1.33 Z2. So this is my input impedance. So I am showing my load at this point. So once you get the load and this is your center, you can draw a circle uh, from this center. You're taking this as center, and this is the on the perimeter like this. This mass is the radius. So you draw a circle like this. So put your compass here, one leg here, another leg here, and draw the circle. So other pencil here and draw the circle. So this circle is called the magnitude of reflection circle. So you got the magnitude of reflection from here. The radius of this will be the magnitude of the reflection. So what I do, so I am taking this radius here and take this radius to the reflection scale here. So this is my radius. So I am taking this mass here. So just take your compass and find the distance from here. So you see the reflection is 0.659. So we got the reflection magnitude from here. It is 0.659, and the angle, if you join a line from center to the load point and tensor rate is up to this, you will get the phase angle from this scale. This is 40 degrees. So you can read from here, it is 40 degrees. So it will get the reflection will be 0.659, the magnitude from this scale, and the angle from the scale written here. So 649 angle 40 degrees. And the standing wave ratio, you can take this radius here and you put on the line. You'll get a standing wave ratio is 4.98. So this is how we can find the reflection coefficient and standing wave ratio. Now if we have to find the location of the generator. So to find the location of the generator, we are now at this point. So we are at this point now, and from this point we have to find the location of the generator. So you see how to this clockwise direction is toward the generator. So from here we have to go toward the generator. How much we have to go? We have to go on 0.8 meter. 1.8 meter is the length of the transmission line, and 1.8 liter will be how much wavelength. So let us find the wavelength first. So it is given u lambda equal to u over f. U is zero point 0.6 times the speed of light, c times 10 to the power 8, and frequency is 60 megahertz. 60 times 10 to the power 6, that is 3 meter. So wavelength is 3 meter. That means 1.8 meter will be zero point 0.6 wavelength. So 0.6 wavelength. So now we have to go zero point 0.6 lambda. So what is the how we have to make zero point 0.6 lambda from here? So just there is lambda scale. You can see the lambda scale is here. So if you start from this point and move a full circle, that will be zero point 0.5. So starting from here, the complete circle is zero point 0.5 lambda. As you know, this is Vmax and this is Vmin. So if you go from Vmax to Vmin, that will be lambda over 4. And from Vmin to Vmax, again lambda over 4. So if you move from one point to a full circle, that will be zero point 0.5. So I'm starting from here and take a complete round here. So that will be 0.5, then go zero point 0.1 more. So if you go zero point 0.1 more, so you will get to this point. So this was 0.195, this value. In the wavelength scale, it is 0.195 wavelength. So if you add 1 here, that will be 0.295. So if you see 295 here, so this is now join the center to this 259 lambda line. So this will be the intersect point will be the generator. So this is your input. So now once you get your input, read the value for R at this point and X this point. So if you go this way, you will get R value, and if you go this way, you will get X value. So R value is 1.8 and X value is 2.2. But as you are at the bottom part of this chart, so it will be negative. Now, if you want to find the regular value, so you have to multiply with the Z naught. So 75 times this is the resistance value, and 75 times 2.2 is the reactance value of the input impedance. Now you have to find YL, the load admittance. To find YL, this was your ZL. you translate this line to the opposite directions, and this line will intersect the circle at this point. This is your YL. You know, the opposite to the ZL will be YL. So if it is ZL here, the YL will be here. Similarly, if you have YL here, the opposite will be ZL. So YL, you got this value is, if you move this way, you will get the R values. If you move this way, you will get the X values. So R value is this, X value is this. Now you divide by Z naught, you will get the normalized value. So it is 0.3.04 minus J 6.47 millisiemens. Now you have to indicate Vmax and Vmin and their locations from the load. So Vmax will be this point. The maximum voltage will be located here and minimum voltage will be located here. Now you have to find the distance from the load to this point. So from the load to this point has distance 0.25 lambda and this is 0.195. In the wavelength scale, you can find the value is 0.195 and this is 0.25. So distance will be 0.25 minus this. So distance will be 0.25 minus this. So you'll get 0.55 lambda. And lambda was 3 meters that we calculated before. So that will be 0.165. So that's the first maximum. And first minimum will be this value plus 0.25 here because the full circle is 0.5. So from here to here will be 0.25. So whatever you got here, add 0.25 with that. That will be a minimum. So minimum is the distance from this point to this point. This point will be 0.5 and this is 0.195. 5 minus 0.195 is the distance from here to here. You cannot measure distance in this way. You have to always move load toward the generator. You cannot move in counterclockwise. You have to move in clockwise always because you are located at the load and you have to measure something from the load side to the source side. So to the source side, you always go clockwise. So you have to find the first minimum here. This then second maximum. So if you start from here, you will come up with one maximum, then you will come a minimum. Then if you complete this route, you will get another maximum here, and keep going, you will get a minimum here, you will get a maximum here, minimum here. So if you want to get second maximum, will be just first maximum, wherever was first maximum plus zero point 0.5, right? Because first maximum you got 0.055, the second maximum will be 0.555, right? Or you can write first minimum plus 0.25. First minimum is 0.95. Okay, so 915 plus 0.75. So you get this one. So just you got 1.65 and plus 1.5, 2.45. Then if the transmission line has 1.8 meter length, so you see the second minimum is 2.4, but the second minimum is 2.4. This is outside of the transmission line. So if you think about a transmission line, think about you have a transmission line like this. This is your load and this is your source. This is your source. Now you will get some, say you have a first ZL is here, you got a maximum at 165. So this is your maximum 165. So this is your maximum. And then you got minimum at 915. So you got a minimum here. So 915. And you got second maximum at 1665. So second maximum at here, and then the third minimum will be somewhere up outside of this transmission line because the transmission line is 1.8 meter. So you got a maximum here, a minimum here, a maximum here, a maximum here, and something here. So you see your first maximum is here, then you got a minimum here, a maximum here, and another minimum that is 2.45, that is higher than the transmission line length. So this is doesn't exist on the line. So there is only two maximum and one minimum on this system. So you have one maximum, two maximum, and one minimum here. So basically, you will come up with like a standing wave like this. So you are starting with a maximum, a minimum, but a maximum, and this is outside. This is not here. And now you have to find the impedance at 1.2 meter. At 1.2 meter means zero point 0.4 lambda. So if from the load you have to go zero point 0.4 lambda. So this is 0.195 and add zero point 0.4. If you add zero point 0.4 here, that will be 0.595. 0.595. So from here you go zero point 0.4. So if you go zero point 0.4 here, so that will be zero point 0.5 here. This is zero point 0.5. Then it reset to 0. So if you move all the way to here, then you have to again move up to this point. So up to this point. So that will be your Z in. Z in will be 0.159 plus zero point 0.4. That means 0.595. But after 595, the system will reset and it will be 0.095. Like for example, if you have a 12-hour clock, that means if you want to, for example, at 11 o'clock, someone uh, invite you to be there after 4 hours. So 11 o'clock after 4 hours, meaning that after 12, the hours will reset to 1, then 2, 3. So you have to be there at 3 o'clock. At 3 o'clock. So just after, not 11 plus 4. You cannot write like 11 plus 4 becomes 15. But 15 at 12 hour clock doesn't show 15. So it goes after 12, it goes to 1, 2, 3 like this. So if someone asks you to go 4 hours later at the 11 and the 11 o'clock, so that means you have to be there at 3 o'clock. 3 o'clock. So 3 o'clock means 11 to 12 is 1, then so 1 hour, then you have to go 3 more hour. 1, 2, 3. So similarly here, if you want to go point 4, so zero point 0.4 means it will be if you 0.195 plus zero point 0.4 is 0.595, but 0.595 cannot be shown found in this chart. So you'll get maximum zero point 0.5 here, then zero point 0.5 you have to go 0.95, 0.95 up to this point. So this is your ZL prime. So that means you have to go on set. So then beyond this point you have to go 0.95 further. And then at this point you can find the R value. R value is zero point 0.3 and X value is zero point 0.6. Then you multiply with 75, you will get this value. So this is how you can find the impedance at any point.